Hello there! In this video, we're going to talk about sine and cosine, focusing mostly on sine, and we're going to give you different interpretations of these trig functions. We're also going to try to explain why, from different points of view, why when x is near 0, sine of x is approximately x. So when you're first introduced to sine and cosine, usually it's with a right triangle. And what happens is we take a right triangle, we put an angle in it, and then sine is declared to be the ratio of the side opposite to the angle over the hypotenuse. And here we go. And cosine is declared to be the ratio of the side, the length of the side adjacent to the angle over the length of the hypotenuse. And this is a perfectly fine introduction to sine and cosine. Note, theta is an angle measured in radians. This is very, very important. So let's remind you what a radian is. So if you have a unit circle, we want to be able to measure an angle somehow. So any angle that you hand me can be placed inside this unit circle. And here's my angle, and I'll put theta in there. All right, so what is the radian measure of theta? Well, if this is a unit circle, then the radian measure of theta is exactly this arc length here. That's what a radian is. So you take a unit circle, you put your angle in the center of the circle, and you see what arc length is defined by that angle, and that tells you its radian measure. That's what a radian is. The upshot of this is that if theta is near 0, so if theta is near 0, then we have this triangle here. It's skinny, and so on and so forth. And we have, well, what's sine of theta? Sine of theta, by our definition, is opposite over hypotenuse, is b over c. Now, if this angle's going to fit inside the unit circle, we should set c equal to 1. And I'm allowed to do this because I can scale the triangle, and that doesn't change theta. It doesn't change this ratio. And if c is near 1, then b, if you imagine this inside the circle, b is approximately the arc length determined by theta. And so that means that sine of theta is approximately theta. All right, let's see another interpretation that's closely related to this first one. So another fantastic way to talk about sine and cosine is again with a unit circle. Here we have our unit circle. And now if you pick a point on the unit circle, say I pick this point right here, then sine theta is the y coordinate. By the way, here's theta, the y coordinate of that point, and cosine theta is the x coordinate of this point right here. And this is a really wonderful way of thinking about sine and cosine. And as you can see, it's basically the same as the last way. But again, if theta is small, so if theta is small, so let's think about this. We have here is theta. Now here's our triangle. Here's theta. I can barely see it. Where is sine theta? Well, sine theta is this height here, which is about this arc length. So sine theta is approximately theta when theta is small. This is another slightly different explanation. All right, now we're going to see a slightly more algebraic interpretation. Another very similar, but still slightly different explanation of sine and cosine is the following. Consider the algebraic expression x squared plus y squared equals 1. This is an equation. It's a relation between x and y. We're using implicit differentiation. We know how to differentiate this. But if you think about that problem, you need to really understand the slope of the tangent line. You need to know points on this curve. You need to know x values and y values that are on this curve. So what are sine and cosine? They're a way of obtaining solutions to this equation. Think about this. If I hand you any value of t, I don't care what it is, cosine t plugged in for x, sine t plugged in for y is going to satisfy this equation. It's going to satisfy this algebraic curve. These are, given t's, the solutions to this equation. It's a slightly different way of thinking about cosine and sine. Now, with that said, again, if theta is small, sine theta is approximately theta. And what's the reason? Well, it's basically the same as this reason right here. Now we're going to see an interpretation that really involves calculus. Yet another way of thinking, this time I'm just going to talk about sine of theta, is thinking about what's called a differential equation. Now, a differential equation might sound really fancy, but all it is a equation with derivatives in it. And so here we start. So f of 0 equals 0. F prime of 0 equals 1. F double prime of x equals minus f of x. Sine of x is the only function that satisfies these three equations. Sine of 0 is equal to 0. What's the derivative of sine? It's cosine. Cosine of 0 is equal to 1. What's the second derivative of sine? Well, the derivative of sine is cosine. The derivative of cosine is negative sine of x. That's the second derivative, is equal to minus sine of x. That's right. And we are not going to explain it in this course, probably, but if you continue taking calculus, you will find out that this is the only solution to these three equations. Somehow, these three equations completely identify everything there is to know about sine. And so now let's ask the question I've been asking. If x is near 0, well, if x is near 0, think about this. It starts off, think about plotting this curve. F of 0 is near 0. This is sine. Sine of 0 is near 0. There it is. So if x is near 0, we've got to be close. F prime is 1. What's the derivative of x? The derivative of x is also 1. So our sine and x are kind of going in the same direction. F double prime is equal, this doesn't really help so much, but think about this. We're going to see that our curve, just by really the first two, has to basically agree with x near 0. So again, sine of x is approximately x when x is small. Now we're going to see my personal favorite interpretation. We have one more interpretation of sine of x, and this one you see in a later calculus class, but there's no reason for us not to show it to you right now. If you parsed all those negatives I put in there, I said we might as well show you right now. So let's do it. So sine of x is equal to x minus x cubed over 3 factorial. 3 factorial is 3 times 2 times 1. Plus x to the 5th over 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. Minus x to the 7th over 7 factorial. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. Plus x to the 9th over 9 factorial. I'm not going to say it. Minus x to the 11th over 11 factorial plus x to the 13th over 13 factorial minus x to the 15th over 15 factorial plus, and so on. Basically, we're just doing every odd number here. And think about this. If x is small, we can't use that pen because it'll be the wrong color. If x is small, then when you cube x, it gets much, much smaller. When you raise x to the 5th, it gets much, much, much smaller. When you raise x to the 7th, it gets much, much, much smaller. All these terms have very, very, very little effect. So sine of x is approximately x. Why are we giving you all these different interpretations? If you can remember this, then it's easy to know what the plot of sine x looks like. Because here I'm plotting y equals x. So sine of x must look something like this. it has to agree with y equals x here. Also, if you think about this limit here, limit as x goes to 0, sine x over x, we worked really hard to explain that this limit is equal to 1. It's really, if you know that sine x, when x is small, is basically x, that's really contains the same information as this limit. Okay, we see a bunch of interpretations of sine and cosine, focusing mostly on sine, but I hope that one of them or more of them stick and really makes you really understand these functions. Okay, time to do some more math.